We present world models for anomaly detection during model-based reinforcement learning inference. Today, learning-based controllers are often kept out of real-world applications due to concerns about their safety and reliability. This is because they tend to respond unpredictably to changing conditions in their surroundings. In this work, we explore how state-of-the-art world models in model-based reinforcement learning can be utilized beyond the training phase to ensure a deployed policy only operates within regions of the state space it is sufficiently familiar with. This is achieved by continuously monitoring discrepancies between a world model's predictions and observed system behavior during inference. It allows for triggering appropriate measures, such as an emergency stop, once an error threshold is surpassed. This does not require any task-specific knowledge as it is purely based on the reconstruction of the incoming observations and is thus universally applicable. This graphic shows the predictions, actual measurements, and corresponding errors for the Walker Walk task from the DeepMind control suite. After half of the time, gravity is increased by 50%. This results in the walker struggling to keep its balance and a clear increase in observation and reward prediction error. A similar experiment is conducted for the manipulator bring ball task. Here, after half the time has passed, the gear ratio of the elbow joint is increased by a factor of 3. The arm thereafter visibly oscillates around the target, producing a clear increase in prediction error, especially for elbow-related state variables. Finally, we also test it with visual observations. Here, a sudden force to the right is applied to the spacecraft in the lunar lander simulation. Measurement and prediction diverge as a result. To validate these results, we similarly apply an abrupt force to a simulated quadcopter navigating the corners of a square. Again, this produces a clearly identifiable prediction error increase for most state variables. After the force subsides, error levels return to normal and the drone continues on its course. We then deploy the trained agent to the real world in our laboratory, where we hit it with a stick to apply the unexpected force. This has the exact same effect as in simulation, showing a peak in prediction errors when struck. Overall, there is a slightly higher baseline error when compared to the simulation, though this is to be expected as the simulation does not model the real world perfectly. In the future, the presented ability to detect deviations from the expected outcome could enable robots of all sorts to self-assess their reliability in any given situation. This could make their autonomous operation in the real world finally feasible. Thank you.